One of Eric's contributions. Well, we'll be the judge of that. Rahul Ilango was now a student at MIT and was an undergrad student doing research with Eric Allender, and that's how he got hooked on MetaComplexity, I think. And he'll tell us more about cryptographic approach to hardness approximating MetaComplexity. Rahul, please.
All right. So thank you, Valentine, and thank you all for coming. So I'm going to be talking about joint work with Yizhi Huang, who's an undergraduate student at Tsinghua. I think he's applying to graduate programs now. So I don't know if those decisions have been made already, but if they haven't been made, he's a great researcher. And this is also a joint work with Hanlin Ren, who you have probably met or should meet if you have not. And, it's a real privilege to be giving this talk on Eric Allender Day. Eric is someone who has been very important to me. When I was at Rutgers, he was really my undergraduate advisor. And so when I was preparing for this talk, I decided to go back through my emails and figure out, when was the first time I actually interacted with Eric? And so I opened up Gmail and I put in from : Eric Allender. And this is a screenshot, you probably can't tell, but there's this little search thing that comes up. It says 1 to 50 of many. And there's so many great emails from Eric, but finally I came back and I searched and I found, what was the first email I actually got from Eric? And it was some bureaucratic thing. I spared you the details of the bureaucracy. It says, hello, Rahul. Sorry, it took me until today to reply to you. And I was like, I looked at the email. I was like, okay, that's interesting. Eric, I don't know how well you guys know Eric, but Eric is extremely prompt at responding to emails. And I was like, okay, how long did it take Eric to reply to this email? And so I looked at the previous message, and it was the previous day. It had barely been 24 hours. And Eric was apologizing to me about doing this. And I think, this is a nice anecdote about Eric. So let me tell you a little bit about how I met Eric and the role he played in my kind of introduction to this field. So in junior year of college, I, by chance, signed up for Eric's class. One of my friends had told me, hey, this class is kind of interesting. Maybe you should take it. And I had a slot in my schedule and I said, okay, why not? Didn't think very much of it. And to say truly the very least, Eric's class had an impact on me. And I still remember my favorite lecture of Eric's was one where, and I don't think I've ever seen in any of the classes that I've taken, a professor more enthusiastic and with more passion for the subject than when Eric, got up, he stood up and he's telling how alternating time and space are dual notions, with alternation, time and space are dual notions. And it was just this exciting place to be where, I was learning about this subject and it was just really wonderful. And so at the end of the class, I really liked the subject. And so, I worked up the courage and I said, Eric, hey, could we do a research project together or something? Is there something to work on? And I remember Eric didn't hesitate, and he was just later that day, I got in my email a list of papers about some strange object called the minimum circuit size problem, which obviously even today is pretty much all I work on. Every once in a while, I venture outside of it. And I think looking back at this time, working with Eric, it's truly remarkable how generous he was with this time. In particular, I would often just go knock on his door at the Hill Center and be like, hey, Eric, do you have a few minutes? And, usually I would spend like the next hour pestering him with questions and, half-baked ideas, really not even half-baked, they're mostly quarter-baked. And I think, of course I appreciate it at the time, but like now, seeing how busy it is, to be a researcher, especially to be a professor, I think what's really amazing is that whenever when I knocked on his door, I asked him, do you have a few minutes? He, said yes. Every single time, which is just in crazy. Like, actually, I'm lying. There was one time he said no. Do you remember? No. He was. There was final exam scores were due that day, and I think he actually sent me an email afterwards. But and that's another thing. Like his emails, is with this one exception actually. You'd send him an email, and the response would be the same every time. It'd be detailed, it would be in line, and it would be usually within an hour from when you sent your email. And I really don't think that like this was like an exceptional thing for Eric. I think this was the dedication he had towards all the students, and I think particularly towards younger, maybe undergraduates who didn't, were new to the field. I think, year after year, Eric takes undergraduate students in this Dymax RU program, which I somehow found my t-shirt from. It says Eric Allender on the back somewhere. There's a puzzle if you want to solve it. And so year after year, he takes these undergraduate students. And in my estimation, few people in the field have done as much as Eric has in giving opportunities for undergraduates to do research in complexity theory, especially undergraduates who otherwise would not have had the chance. And so, in short, I'm very grateful to Eric, and I want to say, Eric, thank you so much. Okay, so now we're all here. There's this question, that Eric sent, was talking about in that first email that he sent me, which was related to the NP-Hardness of MetaComplexity. And so, this is a very important question, whether certain metacomplexity problems are are NP complete, and there's a whole metacomplexity zoo of problems like time-bounded Kolmogorov complexity, conditional versions, whatever. This is a long-standing open question. And one thing that's interesting that has happened over, has really been developed, especially with Liu and Pass in recent years, is this connection or ideal hope-for connection between the NP-hardness of metacomplexity and cryptography. So in particular, there's this holy grail idea that if you could show the NP-hardness of metacomplexity, maybe that gives you a way for basing, let's say, one-way functions on P versus NP. Somehow these NP-complete, NP-hardness of metacomplexity might be related to these fundamental problems in cryptography. And so this is something we've heard a little bit about. Rahul talked about it in the first talk here. And if you've been around for the workshop, this is something that's mentioned a lot. And I want to say, we have this perspective, NP-hardness might help cryptography, but ask not what NP-hardness can do for metacomplexity, or sorry, metacomplexity can do for cryptography. Let's ask what cryptography can do for the NP-hardness of metacomplexity. And this might seem a little strange at first, but actually there are already some works that do this. I think maybe they haven't been discussed so much yet. There's this one great example we have heard about maybe a little bit, Shuichi in this breakthrough work last year showed that this problem MCSP star, which is so close to MCSP, is NP-hard. And that was using information theoretic cryptography. It's using this idea of secret sharing. It's using this idea of one-time encryption schemes. These are really cryptographic notions, although they're in the information theoretic setting. In this talk, that's not what we're going to be talking about. We're not talking about, I'm not asking about the information theoretic setting. I want to ask, can computational cryptographic assumptions tell us anything about the NP-hardness of metacomplexity? And in some sense, the results that I alluded to earlier on the slide do say something about this. You know, this seems like a kind of strange thing, because usually when you have cryptography, it tells you that problems are intractable. It doesn't say that they're NP-hard. You know, you have a one-way function, you have an encryption scheme. It's hard to break the encryption scheme. It might not be NP-hard to, you know, like breaking the encryption scheme doesn't mean SAT is solvable. You know, it just means there's some assumption that's broken. But let me give you an example of some of the results that are known along these lines. And so the first theorem I think you can kind of say, and this is basically implicit in Kapinets and Psi, and maybe, you know, once you see the proof, this theorem is not going to seem so interesting. But there is something maybe there that you can take away. You know, what's the most general notion of NP completeness that you could possibly care about? It would be something like this: MCSP is in P if and only if NP is in P. You know, that's like it's, you know, it may be a bad notion of NP completeness, because then things that are really don't like any problem that's not in P would be NP complete in the real world that we think. But okay, here's like a very simple proof of this. If one-way functions exist, then you have this like extremely this implicational NP completeness. Well, if one-way functions exist, then P is not equal to NP, and MCSP is not in P, right? Which is, you know, I'm not going to tell you how to do that, but that's something that you can do. And so, like, you know, in some sense, cryptography is showing that this is like implicationally NP complete, but it's not clear what the takeaway is. And from this, really, it seems more like this is saying if cryptography exists, then both these problems are intractable. You know, like it's not really saying that you have some sort of NP completeness relationship between the two. And there's another result by Russell, Valentin, and Ilya Volkovich, which says if indistinguishability obfuscation exists, then, well, I'm not going to explain to you what that is, but that's some high-powered, really nice cryptographic object. Then you get MCSP is in ZPP if and only if NP is in ZPP. Again, some sort of implicational version of NP completeness. But again, the takeaway is a little murky, because, like, you know, what is this really saying? It's a bit unclear. So I'm not going to give you the proof of this, because I would need to define indistinguishability obfuscation. You know, that it's a 45-minute talk, and I spent a few minutes talking about Eric. But what I want to ask is, let's ask a different question. Instead of asking if computational cryptography can help us prove like these implicational NP-hardness, what if we ask about the standard definition of NP-hardness? You know, can cryptography help us prove the usual black box notion of NP completeness? That is, like, can cryptography tell you if you have an oracle for one problem, you have like an oracle for another problem? You know, and this seems like a kind of weird question. It seems like maybe this, when you first look at this might seem a little strange. Like, cryptography is proving some sort of black box NP-hardness result. Oh, is it clear what I'm saying when I say black box? Is anybody confused? I just mean like the usual, if you have oracle for one, you have oracle for another, like many one reduction. Okay. And so what I want to convince you in this talk is that in some cases, the answer to this is actually yes. And in fact, it's not as strange as you might think. Okay, so this is my goal for this talk. This is what I want you to take away, besides the fact that Eric Allender is a wonderful and amazing person. Okay, so let me tell you a little bit about this, maybe make things more concrete. I'm going to tell you about two cryptographic objects. In fact, actually, I'm not even going to tell you what they are yet. I'm just going to tell you what they're named. So the first one is this thing called witness encryption. Yeah, I'm going to give you a definition of witness encryption later. But for now, basically all you need to know is that it lets you somehow get a lockbox using some formula. You have some SAT formula phi, and you can lock things up. And the lock is basically the SAT formula phi. I'll explain it later. And there are some results about witness encryption. In fact, it was proposed in this paper by Garg, Gentry, Sahai, and Waters. And they proposed this construction that, if you look at it, it shows that it exists in some ideal model. And then recently, using this work of Jane, Lin, and Sahai, you can show that witness encryption exists under well-founded assumptions. So this is just some cryptographic thing. These are kind of really standard. I mean, okay, I'm not a cryptographer, but my understanding is that these are standard things that are known in cryptography. Okay, and then there's this other object, snargs. I put an I here because snargs are somehow corresponding to short witnesses. So, and there's some really, one of the foundational results here is that they exist in some random Oracle world. So here are two cryptographic objects. If you're a cryptographer, these are things you are very familiar with. And it turns out you just squint at these three results and you turn your head and really, Garg, Gentry, Sahai, and Waters, Jane, Lin, and Sahai, Silvio Macaulay, what they did is they showed that actually some metacomplexity problem corresponding to the cryptographic object is black box NP-hard. And this is what I'm going to tell you about. And in fact, the reductions are like almost syntactic. It's kind of crazy. And so at least in these cases, you have that this cryptographic object and the NP-hardness of metacomplexity are two sides of the same coin. Okay. So let me tell you about one of these results. We'll start. And the metacomplexity problems that we're going to be talking about NP-hardness for are these conditional metacomplexity problems. Oh, are there any questions so far before I talk about this? Either I am very done a great job explaining, or I've lost you all completely. So one is this version of conditional circuit complexity. And so CC here stands for circuit complexity. And you could ask, what's the circuit complexity of computing one function given access to another function? So you have some really X and Y here are truth tables of some function. You can ask, if I have gates that compute one function, how hard is it to compute gates for the other function? So this is some conditional complexity measure. Does it make sense? Okay. And then another conditional complexity measure you could have is conditional time-bounded Kolmogorov complexity, which now, instead of talking about circuits, you talk about programs that run in time t, and you're given a random access, RAM access to y. Two conditional metacomplexity problems. And so we knew for this first problem that it's NP-hard up to roughly a log n factor. And then Lun and Pass showed that this is also NP-hard to a log n factor, and actually showed that on the uniform distribution, this problem is equivalent to one-way functions, but that's not the focus of this talk, so I'm not going to go into it so much. And then it was later improved to this n to the 1 over log n factor by Hirahara, and this was based on some information theoretic cryptographic ideas. And one kind of aspect of this result, whereas if you look at all these proofs, they all work in the regime where the time bound is in some sense sublinear. You have this conditional string y, but your circuit is so small it can't access all the bits of y. And your RAM, you have RAM access to y, but again, you can't access all the bits of y. Oh, did I say this backward? Oh, yes. Sorry. This is wrong. It should be the time is much less than the length of y. And you might think, okay, well, this is just some aspect of the proofs. This is what we know how to prove. Maybe why, whatever. We've solved the problem. Let's move on. But kind of interestingly, Hirahara showed that actually this question, sublinear regime versus superlinear regime, is actually really interesting. In particular, if you could show conditional time-bounded Kolmogorov complexity in the superlinear regime is NP-hard, then heuristica, which is this world where SAT is hard in the worst case, but easy on average. That didn't make sense. You can ask that man over there. He defined it. then heuristica doesn't exist. So somehow this distinction between linear, superlinear, and sublinear seems to be very important. Okay, that's the background on what we previously knew about these metacomplexity problems. And now let me tell you how this object, which is witness encryption, implies some interesting things about these conditional problems. So the first theorem we show is that if subexponentially secure witness encryption exists, which is something, if you're a cryptographer, this means something to you. If you're not a cryptographer, this is something we believe on computational assumptions, based on well-founded computational assumptions. That's all that matters. Then actually it's black box NP-hard to distinguish the case where the time-bounded Kolmogorov, the conditional time-bounded Kolmogorov complexity is like some small polynomial in n versus almost maximal, like constant away from maximal. And the crucial part here is that now we're in the superlinear time regime. So previously, like the yes and the no cases, you couldn't let yourself read all of y. But it turns out if this cryptographic object exists, then you get pretty much ideal hardness of approximation. You can't actually hope for hardness of approximation lower than this under like NP-hardness. Otherwise, you get like a sub-exponential time algorithm for SAT. But if you modify the assumption slightly, you could get. So this kind of shows that sub-exponentially secure witness encryption implies black box NP-hardness of this problem. And in fact, oh yeah, I emphasized this already. And in fact, what this shows is that under plausible cryptographic assumptions, the problem that Shuichi shows its NP-hardness would eliminate heuristica is NP-hard. So in fact, like it's kind of this interesting state of affairs. We know the reduction. You believe these cryptographic conjectures, we actually already have the reduction that shows that this thing is NP-complete. And that if that thing is NP-complete, then we eliminate heuristica. But of course, you have to be careful about this because, like, all right, we're assuming sub-exponentially the strong cryptographic object. If you assume that cryptographic object, then heuristica doesn't exist anyway. So, like, oh yeah, you have a question?
The reduction doesn't rely on this witness encryption, like it's a fixed algorithm?
Yeah, actually, that's a good question. I don't know if there's like a universal witness encryption thing, but you can take the construction that Jane, Lin, and Sahai, yeah, and then plug it in, probably it works. Actually.
There's universal I/O, which implies.
I see. Okay, yeah. So I guess there is. Oh, but is it clear that
it's
I/O and the witness encryption?
Yeah. But you could replace the assumption by sub-X secure I/O, right? And then
then it would be. Although, like, I guess you were saying this the other day, maybe it seems like witness encryption might be a significantly weaker object. Like maybe you can get it from like DDH. Okay, anyway, let's not. Okay, but okay, so this is a result. It's cool. Now we know. I would say, okay, at least now I think I know that the ground truth is that this problem is black box NP-hard. But at least for the purpose of, eliminating heuristica, it's not clear what this means. And you might be like, okay, how interesting is this? We have some conditional result. It would be really nice if you can get something unconditional. But that sounds really difficult because, like if you're using a cryptographic assumption, it seems like you'd only be able to prove NP-hardness, assuming that cryptographic assumption. What's surprising is you can actually use this ideal, like this original construction in the paper that proposed witness encryption. They have this like construction that says, well, if things were ideally like something, then this witness encryption exists. And you can use that to unconditionally show some NP-hardness for circuit complexity. And this kind of gives the best known hardness of approximation for this problem. And one thing, and I'm going to mention, okay, actually, let me mention that later. So this is the description of the two theorems. Are there any questions? That's a great question. Yeah.
Repeat the question.
So, sorry. The question is, here you're showing that some cryptographic object existing shows a problem is NP-hard. Can you get an equivalence? This problem is NP-hard if and only if some cryptographic object exists. Is that your question? Yeah, I think that's a great question. So I think might be some ideas for doing this. Maybe we can talk about it offline. But, yeah, I think it's definitely a good question. Any other questions?
N is like.
Oh yeah, that's a good point. And so n here is going to be like the length of x, and
Theorem 2.
oh sorry, theorem 2. N here is going to be like some polynomial, or I guess it's the length of x, and then y is some poly n.
So we think of X as like a truth table, but we want.
Yeah, that's true. And here is going to be x is a truth table, y is a truth table. And I should say in this setting, we're back into the sublinear regime, because this is an unconditional result, so you wouldn't expect, maybe you wouldn't expect it to be. Valentine, when did we start? How much time do I have? Okay, it's the query will be, Oracle query will be
20 minutes.
20 minutes, yeah.
So what is the,
just in the definition of CC of X given Y,
Yes.
what's the access of Y in that model?
The access is that you get a gate in your circuit, and that gate is going to compute the function described by Y. Does that answer the question?
following up on the potential equivalence question, so the ideal model that you're using is ideal graded encoding. What is the ideal model? So the potential equivalence is between unconditional witness encryption graded encoding and NP-Hardness.
I see. I don't know if that was the original question, but that's like, I think maybe the original question was like without the ideal world, but with the idea. Okay, let's talk about it later. Yeah, I think.
Because
in this case, I guess you get an equivalence.
Seems unlikely to build, but to use the NP-Hardness to get a construction in an ideal model seems much more likely. We have such examples even for witness encryption, right?
I see. Yeah, that seems reasonable.
For theorem 2, what should I think of the length of y as being?
Some polynomial in n. So x is of length n, y is going to be of length polynomial in n.
So why is it sub?
It's because like if the circuit has only has complexity n to the 0.49, that means you only made n to the 0.49 queries to y. And so if y is of length, let's say n to the 100, it's a sublinear number of, you've only read a sublinear number of bits. Does that make sense?
Yeah, but this will work also for larger and larger. So what's the restriction that you mean by sublinear? That the circuit always work in sublinear time in the input length?
Okay, so it's sublinear in the sense that you've only queried a sublinear portion of y. That's what it means. It's not like sublinear circuit. Okay, cool. Now let me tell you what witness encryption is, because I haven't said that yet. And hopefully this is a really cool object. So as far as I know, I'm not a cryptographer, but as far as I know, it was first proposed in this paper. Roughly what witness encryption enables you to do is something along the lines of the statement. Suppose you have some message M, and you only want to be able to send that message M to people who have a proof that P is not equal to NP. In fact, actually, I'm lying a little bit. You really need a short proof that P is not equal to NP, but let's forget about that. So suppose you want to do that. Witness encryption is some object that lets you do this. In particular, the setup is as follows. You're given some formula phi and some message M. So this is some stat formula phi. And you can map it to some encrypted message. This is like the lockbox based on phi. And you have the following guarantee. If someone happened to have a witness that phi is satisfiable, then there's some polynomial time decryption procedure which takes this encryption and spits out the message M. And the other condition you have is that if phi happens to be unsatisfiable, then this encryption, I'm lying here a bit, but let's just pretend it's pseudo-random against adversaries running in a lot of time. And actually, there's a couple of things I want to mention here. First, let's forget about this running time part, because that's related to subexponential security. There's actually a gap here in terms of, well, ideally what you'd want is you'd want to say only people with a witness can decrypt. This is not saying that. It's saying if you had a witness, you can decrypt. If it happens to be unsatisfiable, then you learn nothing. It doesn't say like if it is satisfiable and you don't know a witness, it doesn't say anything about that. that's some cryptographic technicality. It's
There's a stronger notion called extractable.
extractable. Yeah, but I guess this is unclear whether it exists or not, right? Okay.
Everything is unclear, but yeah.
Yeah, there's a stronger notion of extractable witness encryption, which would give you this, but you know, let's not talk about.
All you need.
But this is all we need. Yeah, this is all we need. And so one thing that's really cool about this encryption scheme, and this is something that we're going to use, is this encryption scheme is going to look pseudo-random, even to adversaries running in 2 to the m to the 100 time. And you might think, well, that's impossible. Like the message is only of length m. How could you be secure against adversaries running in 2 to the m to the 100 time?
The amount of randomness you use for
Yeah,
encryption.
exactly. The point is this encryption is going to be of length much larger than m. So now you're safe. Okay. So this is something that I'm going to come back to later, that will be used later, that like the running time here actually that you're secure against is massive. So if you're confused by that, you should ask a question now.
How does the length of m relate to the length of the formula?
Let's say the length of the message is some polynomial in the size of phi. But yeah, you can state this with what you do is you say you can encrypt a bit, and then once you can encrypt a bit, there's the natural way to concatenate. So. Oh, yes.
I thought I had something. Why would they want to instantiate something that's satisfiable?
Right, because you don't know. I don't know if P is not equal to NP, right? But let's say I want to send a message to someone such that if they could prove it, then they could decrypt the message.
I'm using a formula that I don't know
I don't
if it's
know.
satisfiable or not.
Exactly. I don't. Yeah, and that's the key point here. I'm not going to know whether it's satisfiable or not.
Just give it a
Or maybe, I mean, it could be a fixed thing. Like it could be some satisfying. It could be phi corresponding to whether its input is a proof that P is not equal to NP. But yeah.
universal for every input, let's say.
Yes. I mean, this is for arbitrary phi. It's some procedure that takes. Does that answer your question?
Try to understand which formula and try to instantiate this.
Oh, it's for any formula. This will work for any formula. In our reduction, we'll choose specific formulas, but okay. Yes, Mike.
Are you going to explain? So what are we supposed to see? You said that only someone with a proof that P not equal to NP is.
Yeah.
Are we supposed to see from the description of this thing that?
Yeah. So this is there's some gap here actually. This is the comment about extractable witness encryption or not. Yeah, because this actually doesn't give any guarantee if it so happens that there was a proof that P not equal to NP, but you don't have a witness, which I think is your question. Okay, the answer to your question is no. So
The answer is no, that you're not going to show us.
yeah, I'm not going to show you. Yeah. Okay. Any more questions? This is great.
But you are saying that if it was extractable with encryption, that we should be able to see why not?
Yeah, but I haven't told you what extractable encryption is, so we have to see. Okay, let's not get too caught up in this if definition. Yeah. So let me tell you how to prove theorem 1. Actually, does anybody here? This reduction is going to be like 2 lines. Does anybody here see how you prove that this is NP-hard if you had witness encryption? A couple of you I've told this to already, so don't raise your hand. But anybody, you have Ian. No.
Well, okay, you're trying to break SAT or something, so you get a formula and you don't know if it's satisfiable or not.
Right.
So just do witness encryption.
Okay, but then what's your instance X for Y? Okay, any? Exactly. Oh, okay. Wait. What did you say? Say it again.
The condition is your message, and the input is your X.
Okay, I think yeah. I think you're saying Y is your okay. Sorry, yeah.
X is your message.
Yeah.
And Y is the encryption using.
Exactly. This object is really syntactically, almost designed to show that conditional time-bounded. I think this is what you're trying to say. Sorry. What you do, you want to show this problem is NP-hard. So given a stat formula phi, the instance you map it to is just pick a uniformly random message that's sufficiently long, generates its encryption, and then just consider message encryption here. And now what's the point? Well, if phi happens to be satisfiable, then, okay, what's a really nice way to describe M? You just hard code in the satisfying assignment and then run decryption on the conditional string. You have access to the conditional string, just do it. And the witness here is only of length n, so you'll get this. I'm hiding some other things here. On the other hand, if phi is unsatisfiable, then the security guarantee of this encryption is so strong that actually, like the brute force algorithm for like checking its yes.
Isn't the encryption function going to be randomized though?
Yeah, the encryption. Oh yeah, sorry. This is a randomized reduction. My bad.
No, but what I'm worried about is okay. Is the decryption also randomized?
Encryption is not randomized.
Oh, okay.
Decryption is basic. Yeah. Okay. Yeah. Encryption.
So,
Is
given the witness. Okay.
Oh, sorry. But even if it was randomized, that's fine. Oh, I see. Okay, but decryption is not randomized.
Oh, okay.
But yeah, but that's important, I guess. Yeah.
It just passed the randomized part.
Okay.
Yeah, we're just worried that it's a little larger than M.
So right. So if phi is unsatisfiable, then the security of this is so long. It is against adversaries that run in so much time that it actually is against adversaries that run in time like way more than the brute force algorithm is. And you know, if that made sense to you, great. If that doesn't make sense to you, oh yeah, sorry, Ian.
Is the security against randomized protocols as well? Like, can you show hardness of RKT or BKT? Or...
Oh, I see. Yeah, you can show that.
Okay.
But the encryption is so strong that actually this thing is going to have to basically require maximum. Does it make sense? At least does the intuition that these two objects are kind of like, you know, you squint at one and you get the other. Black box reduction of the other. Hopefully that's clear. That's what I want to convey to you. Okay, so now how do you prove theorem 2? This is unconditional. Well, this original paper of Garg, Gentry, Sahai, and Waters, you know, these guys are, as far as I understand, real cryptographers. You know, they love crypto. I don't know if they really care about metacomplexity, but what they did, I didn't realize it, is, or maybe they did realize it, I don't know. They actually showed this theorem, really. So they give this candidate witness encryption scheme based on multilinear maps. You know, they didn't state this in the paper, but you can show that this scheme is secure in some generic Oracle model, and where you had like an ideal multilinear map. So now what are you going to do to show this theorem? You just you take this model and you put it into the string line, and then you just run the reduction as before. So literally, actually, these security in these ideal worlds unconditionally show this complexity theory application. Does it make sense, or at least? Yeah, well, I think what's really cool here is that, like, you know, once you know these objects, it's actually like the jump from the crypto to proving this results is not really that hard. It's really just a matter of perspective. Yeah.
Does something, okay, I don't understand cryptography at all, but does something interesting happen with randomized versions of KT? You put like a random oracle into the condition string? Because as far as I know, there's a bunch of random oracle results in the crypto set, right? And is there a natural way to line that up with it, just like
that's a good question.
But I don't think this is the Oracle construction is a random Oracle because, you know, encryption would allow you to do secret agreement, for example.
Right. Yeah, it's a good question. Let's all right. So some things, how much time do I have? 5 minutes. Okay, cool. So let me highlight a few things that are kind of interesting about this. And these are things that I think, you know, we as authors don't yet understand, right? Yes. One cool thing about here is that here you get pretty good hardness of approximation, which is strange because usually when you get hardness of approximation, there's a PCP in there somewhere. And here, you know, we're not really using PCPs. I mean, we're using this GGSW scheme, but is there some PCP hiding in here, or is there something special about this problem that lets you get this hardness of approximation? I don't know. It seems like an interesting question. Another interesting aspect is this notion of secret sharing schemes. I mentioned earlier that Hirahara has this result, which is for a related conditional problem that doesn't quite get this level of hardness of approximation, gets this n to the 1 over log n. And that's based on information theoretic secret sharing. And somehow, so you can show that witness encryption is basically, is it equivalent or it implies equivalent to computational secret sharing. So what's going on here? We have one result. I see. So we have one result, which is using information theoretic secret sharing, and it gives you some hardness result. You have another result showing computational secret, which is basically assuming using computational secret sharing. It's giving you another result. I don't know, something interesting is probably happening here. And so I think one thing that's cool about, actually, these two are things that we don't understand. This one, I guess we kind of understand, but it's kind of interesting that security in cryptography, you have these ideal models, and sometimes it's not always clear what the takeaway is. But actually, security in these ideal models, at least in this setting, is giving you like rigorous applications, consequences in complexity theory, which is kind of fun. All right, so I probably have like 3 minutes now, right? Or 2 minutes. So I'm gonna really quickly, no, I'm not. You can define MCSP on relations. There's some way to do it. Let's not worry about it. But you could define MCSP on relations. And it turns out that we actually already know this problem is NP-hard based on some of Shuichi's work. But if you want to get better hardness of approximation, you can get better hardness of approximation using snarks. Now, what is a snark? Well, okay, I'm not gonna, sorry. If you had snarks, you can get better hardness of approximation. That leads to some theorem. Let's not talk about the theorem yet. I don't want to convey the idea to you, which is that snarks are somehow related to some version of MCSP.
You need snarks in the plane model, right? You cannot rely on the.
Yeah. So exactly. But then, Okay, so if you had snarks in the plane model, snark is some cryptographic object. Oh, right. There's a whole joke here about I was going to be like, oh, you need some very smart prover over here, and then you need some kind of dinky verifier over here. Okay, but well, I'll skip that joke. It's like, okay, all right. Yeah, okay, you can read the paper. But there's, but just like the other reduction was like 1 line, and it turns out that the reduction between this is also 1 line. So there's basically what you do is you define a relation that is consists of the truth table of the verifier run on a random string and pi with phi hard coded in, if you know what that means. And the reduction, basically goes through if you have subexponential security. So just to recap, here are some examples where you have this 2 sides of the coin, where there's some cryptographic object and its existence is implying black box NP-hardness of metacomplexity. You have these examples, witness encryption and snargs. So thanks for listening to this talk. And
Other questions?
So I have a question. So
Where is the loss in your NP-hardness for MCSP with like a conditional truth table? Because you have like square root of n loss.
yeah, let me just go back to the theorem statement so it's clear to everyone. So, ideally what you would like to show is that this is n, and that's, or maybe n to the 0.99, and that's n to the 0.01. And there is some loss coming from some technical factor that we actually think we're hoping to remove before. Okay. The paper online. Actually, that's a good point. If any of you are interested in the paper, just send us an email. It's not online yet, but we're happy to send you a draft. It should come online in the next. Hopefully. Yeah, I hope so. But one of the things we want to try and nail down is we want to get this to n to the 0.99. But there's some technical aspect. I don't know, Alan, is there some succinct explanation for the technical?
I also forgot, but I think the n to the 0.99 is more natural. But we need to do some technical.
Yeah, it's like, yeah, okay. Well, it seems like some technicality. It's probably provable to end before that.
Thank you, Rahul, again. Off the line at 2:15.